Alright, so we're going to start now, and this will be the start of your blue book. It's the very first page. And unfortunately today is just a bit of housekeeping, so to speak. We're just going to be talking about some things that are specific to physics. And here's the skeleton on this page that we're going to talk about. So we'll talk a bit about problem solving, units, precision accuracy, sig digs, graphing, and that kinematics, dynamics, and 2D vectors is Unit A. So this is where we'll actually start. Probably next week we'll start it up. So all this at the beginning is sort of just preamble to get you guys warmed up. So problem solving. So in physics, it's basically all problem solving. There is nothing else to it. Aside from some graph work in the lab, this is pretty much the entire course is problem solving. So if we go through this, hopefully you can read it on your page and highlight some keywords. It says, first decide which physics ideas are relevant to the problem. That is probably the most important thing. Am I doing uniform motion? Am I doing non-uniform motion? In the sense that, is the object accelerating? Is the object not accelerating? Does this relate to force of gravity? Are there other forces involved? So that's probably the hardest part, is just knowing the physics principles and then applying them. Okay? And it says, don't skip this step, even though it's the most challenging part. Like, nothing in this life is free. You have to work for anything you want to be successful at, and it's going to be hard at first, and you can't skip this. So a lot of people will skip this, and they just memorize certain procedures, and then they hope that it's the right one, and then sometimes that doesn't really lead to proper understanding. Okay, so identifying a target variable, that would be like if the question says determine the acceleration of the system, you're like, okay, well I need to find acceleration. So that's not too difficult. You just got to make sure you're reading properly, and then you're going to probably be doing some algebra like on the sideboard there. Down at the bottom here, identifying and setting up the problem, choosing equations. So you'll have a formula sheet, and on that formula sheet I'll have you make little marks on it, like, okay, this formula's for this formula's for this, and so on. So you have a formula sheet that you make all these marks on, but then when it comes time for the exam, you get a fresh formula sheet with nothing on it. So you have to have studied your formula sheet. Okay, then of course you're probably going to want to draw a picture. Does it have that on there? Choose equations. Most often you're drawing a picture. Most often. And then you do the math, basically. And then when you finally get to your answer, it's often wise to think about the validity of your answer. Sometimes you'll be talking about force, and maybe you'll be talking about decelerating a car and the force of friction that it takes for that to happen. And if you get something like really small and the car is really heavy, does that answer even make sense? And then if your answer doesn't make sense, maybe did I make a mistake, and you go back and fix it. So problem solving for math and physics, it's huge, and it's going to be key to your success. In your physics homework, the units, you can get lazy with them, especially like when you're doing the math. You don't have to necessarily put all your units in, but for units, you need to put at the end of each solution the proper units. At the end of each solution, put the proper units. So if you're doing speed, you put meters per second. Okay, if you're doing time, you put second. If you're doing force, you put Newton. So if you have the improper unit, you will get docked marks, and it's not a huge amount. So it'd be like, if you got your units wrong on the test one time or more, you lose a half a mark. So if you screw up the units like 6 times, you still only lose a half a mark. You get docked once per test. And also you'd get docked for rounding once, and you'd get docked for significant digits once. So you could lose up to minus 1.5 per exam if you're not careful. And if the exam's out of 30, you know, it's a decent size mark that you're losing just for not being careful. So these are the standard units, so to speak. So you can put the word standard there. So we use second for time, we use meter for length, and we use kilogram, we use kg. So just note that it's not the gram. Mass is, you don't use gram, it's kilogram. So kilogram is your standard unit for physics, for mass, length, and time. So these metric prefixes you have to know. You'll have a formula sheet though, which will have them all. So you're not typically forced to memorize these, but after doing a bunch of physics, you'll end up just knowing them. So in terms of length, the kilometer, this is like if you're measuring long distances, like from here to Calgary, it'd be a few hundred kilometers. And then typically they go in powers of 3. So the next to the kilometer would be the meter. So like if meter is here, then you'd go 3 jumps to the kilometer. So 3 powers of 10, right? You need 1,000 meters to make a kilometer. You can see right here, you have 10 to the 3 meters, 1,000 meters. But there are some specific ones that are used that are not within the grouping of 3, and namely those are the centimeter and the millimeter. Okay, so you see how it's 10 to the minus 2 for centimeter. That means it's just 2 to the left of the meter, so that's centimeter. And then one more over, that's 10 to the minus 3, that's the millimeter. And I think most of you at this point in your life are like, this is a breeze, and it should be at this point, especially kilometer, centimeter, and millimeter. Now some new ones that you might not have heard about, you have the micrometer and the nanometer. So micrometer will be 10 to the minus 6. Notice it's groups of 3. So once you pass centimeter, millimeter, they no longer care about like specific ones in between. It's every group of 3. So micro minus 6 and nano minus 9. Nano is very small. We're talking about the size of like carbon atoms. You can get all the way down to like 10 to the minus 15. This is femto. This is like size of a single atom, like it's tiny. So we rarely get into that in Physics 20. Okay, now jumping to mass. Typically you only see gram and milligram. I rarely see microgram. You won't see microgram. Okay, and this symbol here for micro, this guy here, what's this guy? I think it's mu. Doesn't really matter. This is how you write it. I think it's mu, Greek letter. Okay, and then they use N for nano. Okay, so make sure you know micro and nano and the symbols that they use it for. All right, I think that's good enough for metric. Okay, unit conversions. I'll just show you this graphic right here. This is by far the best way to do any type of unit conversions. All it's called is unit analysis. That's all it is. If I want minutes to be in seconds, all I have to do is put minutes in the bottom and seconds in the top, and then figure out whatever the relationship is and multiply. So this you have to think about, or use a formula sheet. But this is very formulaic. If I want minutes to go away, put minutes in the bottom, it'll cancel, and then whatever I want goes in the top. And we'll do some the most common for us would be like kilometer per hour to a meter per second. So why don't we do one of those? Let's do it at the bottom of the page. So let's just do something pretty familiar, like 60 kilometers per hour. This is like, you know, the speed limit on a city road. I want to get it to meter per second. I want meter per second. This is what I want. I want m over s. That's the goal. So right now, what's in the bottom for time? And I want seconds. So I get rid of hours. So where do I put hours? Just worry about units right now. H goes up, top. Can I think of a relationship that can get me into some other unit of time? In 1 hour, there's 60 what? In 1 hour? 60 minutes. Notice the hours are now gone. Now I'm in kilometers per minute. Not what I want, right? So get rid of minute, get rid of minute. Put minute up top. Now, what could I put down here? Second, right? Is there a relationship between minute and second? In 1 minute, there are 60 seconds. So now I'm in kilometers per second. If I want kilometers per second, all I have to do is divide, start with 60, right? Start here, obviously. Divide 60, and then divide 60 one more time. That would be kilometers per second. But I don't want kilometers, I want meters. So I got to multiply by one more thing. I want kilometers to go away, so where's it going to go? In the bottom, because I got kilometers in the top. And I could put meters up top. What's the relationship there? In, which one's larger? Kilometer, right? So in 1 kilometer, how many little meters could I get? 1,000. Okay? So take out your calculator, go 60 divided by 60 divided by 60 times 1,000. Yeah. You guys get 16.6? So you notice that 60's in the bottom, 60's in the bottom, and the 1,000's in the top? That means if I start here with 60, divide 60 times 1,000. Because the 60's are in the bottom, right? So you're timesing by a fraction where 60's in the bottom. You can times by 1/60th, but it's really just divide 60. Yeah. Okay. So does anybody know the shortcut here? What is 60 times 60? 3,600, and then you have a factor of 1,000. So really it's just 3.6. That's the factor. 3.6. So in this case, you can memorize this if you like. km per hour to meter per second. All you have to do is divide 3.6. That one's so common that you just memorize that. And just word of advice, you never want to go meter per second to km per hour, typically. The word problems that you'll get in your homework, they'll make you start in km per hour, but that's not a standard unit. So then they'll make you go to meter per second. So if you just memorize that it's divide 3.6, you're pretty much okay. But you should know this unit analysis because you'll have other situations that you'll have to use it. Okay, and this is another example of that you could read. Okay, so precision and accuracy, this is something I'll just go over quickly when we do labs. I'll briefly mention it again. Like when you go into the lab and you do some measurements with like a ruler or your stopwatch or something like this, there's always going to be some amount of error because humans aren't perfect, your tools aren't perfect, and when you do your physics, you have to make mention of that. Like there is some degree of uncertainty. So like our ideal equations might not work out exactly how we want them to because there is some error involved. Okay, so precision and accuracy, the first thing you should just mention is that measurements always have uncertainties. Okay, unless you're like at the U of A using the most modern equipment, like there's going to be a significant amount of error. So like if you had a ruler stick, let's see if I have a picture of this. I'll just pause the video and I'll hand out a diagram. Okay, so if you measure the thickness of a cover of a book using an ordinary ruler, your measurement is reliable only to the nearest millimeter, just like how we had it. So we could only go to 2 decimal places. And the second decimal place has uncertainty. So when I go 4.15, this one here, this one's uncertain. Okay? So, yeah. And then later, like if you took physics at a university level, you would have to do mathematics on the uncertainty. Okay? And we don't really take into that, we don't take that into account in high school in Alberta, so you don't really have to worry about it too much. And what I mean is this stuff down here at the bottom. So right here where it says this plus or minus this 0.02, we don't do any of that. It's a little bit beyond what's expected. Okay, so yeah, we'll just move on because that's enough. So what we were just talking about is accuracy, that uncertainty. That's how accurate are your tools. Now precision is a little bit different. Or pardon me, what we were just talking about is precision. The last slide is all about precision. How precise is your tool? Okay, it doesn't necessarily mean that it's accurate. Like maybe my ruler stick spent some time out in the hot sun and it warped and it's no longer a proper centimeter. So then it's not accurate. Even though my ruler is quite precise, I can get to at least 2 decimal places, it might not be accurate because maybe it was out in the sun getting boiled and it warped. So there is a difference between precision and accuracy, and I think that's enough. Where you in Alberta in this Physics 20 have to be worried is this significant figures, and we call them significant digits, or sig digs for short. And you essentially really only ever have to worry about what's on the top left. Okay, so please up here put a little note or highlight that. Essentially all you're really worried about is the timesing and dividing, because most of our formulas, that's all they involve. We will talk a little bit about the plussing and minusing, and it'll be just for your first quiz on this. You can see it in your quiz in front of you. But really, what you need to memorize is this one here. No more than in the number with the fewest significant figures. And we'll talk about what a significant figure is in a bit here, but I want you to take a look at these 2 examples. In the first one, you have 0.745. How many sig digs are in this expression? There's only 3. That 0 on the left is not considered significant. How many sig digs here? 2. How many sig digs here? 4. And then in your answer, how many sig digs? 2. It has to be the same. Whoa, what just happened? It has to be the same as the lowest amount. So if you only have 2 sig digs, that's as most you can have in your final answer. So your final answer can only be the same as the lowest amount. Okay, look at the next one. 1, 2, 3, 4, 5, 6. 1, 2, 3. This has 6. This has 3. Look at the answer. It only has 3. Okay? So sig figs or sig digs, make sure you know this one. This highlighted multiplication division, that's the most important one. And it's not too hard. You finish your question, you get your final answer, and you have all this accuracy. And then you go back into the question and you look. You just do a quick scan. Okay, 2 sig digs, and then you write your final answer. So it's just like a clarification thing at the end. Now for addition or subtraction, it has to do with uncertainty. So your final answer cannot have more certainty than any one of these in here. So let's take a look. This one has how much certainty? 3 decimal places. This one only has 1 decimal place. This one only has 2 decimal places. So in your final answer, how much certainty do you have? Up to 1. So like that 27.153, it's very, very precise. 3 significant figures. The 1174, also quite precise. But this 138.2 is the least precise, and because you're using all 3 of them, your final answer cannot be more precise than any of these ones. So you have to go to the lowest possibility. Precision of 1 decimal place, you have to stay there. Okay, so you guys can go ahead and try this in the quiz. It's just number 3 and number 2. Just try number 2 and number 3 on your quiz right now. So scientific notation, this is an absolute must, just in the sense that sometimes the numbers are just way too big or way too small, and you have to find a way to express it and communicate it properly. It's all about communication, this one here. Because nobody wants to read 384 million meters. They just want to see the 3.84 times 10 to the 8. So let's focus in on this. Right now the decimal is way over on the right, and you can count 3, 6, 7, 8 decimal slides, and you can see the 3.84, and there was 8 decimal slides. And we use a positive 8 because we want that 3.84 to be very large. Positive 8, we're going to put on zeros to the right. If you put in a negative 8, then it means 3.84 times 10 to the minus 8, that decimal would go 8 to the left, and you'd have a really small value. Okay? Now, just a word on this coefficient. It's always, I'll call it, let's call it C. It will always be between 0 and 10, strictly. You never have like 35 times 10 to the 8. It's always a digit between 0 and 10. Okay? So 1.3, 6.7, 8.1. Okay, never 36.2. Okay, it's always between 0 and 10. So graphical analysis, this will occur from time to time throughout the year. Most often you will have a independent and a dependent variable given to you. In math it would be like input output. Science, you can use manipulating responding. So you can see here that on the title of this graph, which you should always have, and you always have this verse in there, and it's basically y versus x. The total mass of the system versus the volume of the sand in the beaker. So if you have more volume of sand, what do you expect the mass to do? Probably go up. And then it turns out that this relationship happens to be linear. So the more volume that you add, the more mass that you get, and the relationship is linear. So the only thing that you really are interested in, usually, is the slope. And to find the slope, what you're going to have to do, and I'll just show you this, like 28, 188. Let's go and find that. That's right here, 28, 188. And you do the rest with all those other points, and you get all these blue dots, And when you do it on your lab, you'll circle them. That's what you'll do on your lab, you'll circle them. And then you take out your ruler, and you do a line of best fit. And when you draw your line of best fit, you actually pick up your pencil, and you don't cross over these circles. It matters later if you take this in university. It doesn't really matter now, it's just getting into good habits. And then you want to find the slope of this line. To find the slope of this line, you have to use two separate points that are not the points that you've used in your data. Okay, so for the slope, use two different points, not your data. Okay, so don't use data points. You have to just pick two random ones on your line, and then you find the slope of that line. You can see you have delta y. Whoa, what just happened? Here's delta y, and here's delta x, and you divide them. Delta y over delta x, this would be 475 over 180. And then you'd figure out this slope, and it would be the units would be in grams per milliliter. So maybe that's interesting, maybe it's not. Okay, so just keep in mind this structure for slope. Say that again. Yeah, we could do an example for slope for sure. And here's some reading that I'll show it to you later as well when we get to our textbooks. I'll come back to this equation of a line. I'll do this equation of a line when we actually have a problem. This mx plus b, you should know this from Math 10, where this is the slope here. This really is emphasized in Physics 30, and you don't see too much of it in Physics 20. And this b here is the y-intercept. So we'll just get to this last slide, and we'll talk about slope. Okay, first of all, I just want to talk about sign of slope. So let's take a look at A. Is that slope positive or negative? Why is this slope negative? Because as you can see, as time progresses to the right, what's the y variable doing? Is it gaining or losing? So as time goes on, it's losing value. So we say that has negative slope. Contrast that with B, which has positive slope. As time goes on, you can see that variable is increasing. What about C? It's got a constant value, so the slope is 0. Okay? Now let's assign some values here and calculate slope. For A, let's figure out what this coordinate would be. What would that be? 0, 5? And what would this point be here? 5, 0. You have an x coordinate, you have a y coordinate. Now to calculate slope, what formula are you using? Rise over run, which is the change in the y divided by the change in the x. Notice it's always second minus first, second minus first. In physics, it's always like final minus initial, final minus initial. And I always say that this is the second point on the right. This is the second point, this is the first point. I always just use the one on the right as the second point. So for A, what would y2 minus y1 be? First of all, where is y2? Well, it'll be over here. Is it good? So we have 0, take away, what's the other y? 5. 0, take away 5. And on the bottom you have, good, 5, take away 0. And then just do them separately. What's 0 minus 5? And then 5 minus 0. And then negative 5 divided by 5 is negative 1. The slope is negative 1, which means that when you go to the right once, you go down once. To the right once, you go down once. To the right one, you go down one. Because there's a little 1 under there that you don't see. 1 to the right, 1 down. 1 to the right, 1 down. And remember, it's rise over run. So rise over run. So for run, you run once, you go down once. Once, once. It's up to you. But just for convention, I always say the one on the right is the second one. You could do this one, and it'll still work out. Okay, let's do B. Let's get some points. What's this one here? 0, 0. And what's this one over here? Those look like smaller increments though, eh? Let's say that's 4, 2. Because they're like half increments. Doesn't have to. Ultimately, I could put whatever value I want in there. But let's just do it here. And I'll use a highlighter here just to show you how simple this is. Subtract the y's, and what do you get? 2. Subtract the x's. Yep. Yeah, it's okay. I'm just picking actually random numbers. Doesn't really matter. So how much did the x change in the blue highlight? 4 minus 0 is 4. Okay, so for the red highlight, that's delta y. Do you agree? And for the blue highlight, that's delta x. So delta y over delta x would be 2 over 4, which is the same as 1/2. So what does the 2 represent? The 2 represents 2 to the right, and then 1 up. 2 to the right, 1 up. 2 to the right, 1 up. Okay, and you can get these triangles. This is delta x. This is delta y. Okay, and you just have this right-angled triangle. That's all it is. Right-angled triangle. Slope. Okay, so that's enough for the slides. Let's go to your quiz.